Attention and neural responses to visual inputs. Attention can be directed at a location different from the current gaze position or at the same location as the gaze position. And this is mostly the case in natural visual behavior. And attention is measured by its effect to increase the performance and speed of a visual task, such as visual recognition, at the attended location versus a non-attended location, or at an attending situation versus non-attending situation. For example, to pay attention to red-colored inputs, or paying attention to objects moving in a particular direction. Attention can be guided to a location by voluntary or endogenous control. For example, here in order to recognize the letter at this location. Or attention can also be guided by external visual inputs, such as when attention is distracted to this location by a sudden flash at this location. Now let's look at how attention affects neurons' responses to visual inputs. These effects are mostly studied under top-down attention, and they are observed in neural activities in extrastriate cortices like V2, V4, IT, and MT. And these effects in V1 are relatively weaker or non-existent. The experimental design is often like this. Here is the display screen. The monkey fixates on the central cross. This dashed box marks the residual field of a neuron being recorded. But of course, this dashed box is only for illustration here, and it's not shown to the monkeys in a visual display. And in this residual field, it contains two visual items, in this example, two bars. And often one of these items, for example, the orientation of the bar, is preferred by this neuron, and another one has a non-preferred feature. And the experiment can also have visual inputs outside the residual field. Monkeys are trained to covertly pay attention to one visual item. Let's say this one. For example, the monkey may be trained to detect any color change in this bar. So presumably its attention is on this bar. And meanwhile, the neural activities are measured while the monkey does the task. So for example, we can see how neural activities depend on whether the monkey is paying attention to this bar, or this bar, or this bar. This way, it has been found that if there are two items inside the residual field, and if the attention is directed somewhere outside the residual field, then the neural response to these two items together is the average of the responses to each of the two items presented alone. However, directing attention to one of the two items inside the residual field makes the neuron respond as if the other item is absent. These neural response changes are not caused by any change in the retinal input, because in all situations, the monkey has to keep its gaze fixated on the central cross. So the neural response change is caused by a change in where the monkey pays attention to. Another experimental design is to have only one item within the residual field and examine the attentional effects. In more detail, let's say this is the response property of one neuron. Its response increases with the input strength within the residual fields. If attention is directed towards this residual field, you can see typically an increase in the response. So the blue curve becomes the red curve. That means attention increases the sensitivity of this neuron. Attention can also change input response curve in other ways. In this case, this is as if attention increases the effective input strength. You can also measure the feature tuning curve of a neuron. So, for example, let's say that this is the orientation tuning curve of a neuron. So the feature value is the angle theta of the bar within the residual field. And here is the preferred orientation. Attention to the residual field can change this tuning curve, for example, to scale it up or to change its shape so that the feature tuning width is smaller, or larger, depending on whether the attention is to this resident field or not. Yeah, and these kind of phenomena is called biased competition, meaning that visual inputs compete for being represented in the brain, and top-down attention to an input item or input feature biases the competition so that more brain resources are used to represent the attended input. So far, only one study showed how neural responses are affected by bottom-up attentional attractions. It studied attentional effects on V1 neurons. This is the fixation stimulus in the study. The monkey fixates on a central point, and this is the resident field of the neuron being measured, and then the exogenous cue flashed after a pause, and the probes appeared. So we can then measure the neuron's response to the probe inside the resident field. Here the probes are just the gratings inside, outside the resident field. And we can examine how the neural response to the probe inside the resident field depend on whether the cue is around the resident field or away from the resident field. This is neural response versus time, and time 0 is when the probe appeared. The darker curve is for when the cue is on and around the resident field, and the lighter curve is when the cue is away from the resident field. And so this cue on is a validly cued trial, and cue away is an invalidly cued trial as far as this neuron is concerned in response to this probe. Yeah, and now before the neural responses to the probe happened, the neuron actually responded to the cue when the cue is on, but not when the cue is away. And you can see the cue appeared roughly a bit more than 100 milliseconds before the probe appeared. However, by the time the probe appeared, the response to the cue has already died down, and the initial response to the probe is independent of where the cue is. However, at around 100 milliseconds after the probe appeared, you can see the response to the probe is much higher when the cue is on the resident field. That means the neuron's sensitivity to the probe is increased due to this cue. Now, however, because the neuron also responded to the cue, even though by the time the probe appeared, the cue disappeared and the response to the cue has already died down, one can never be sure whether this increased response is not actually due to this cue. Yeah, the cue may be a confound, we can't be sure. Yeah, and so one way to resolve this is to simultaneously flash two cues, one on the resident field and one away from the resident field. In this double cue case, the neuron responds to the cue inside its resident field as it should, but there's no enhancement to the probe. So therefore, just having a cue to the resident field is insufficient to cause a probe enhancement. It also requires no competition from the second cue for attentional attraction to the resident field. Although top-down attentional inferences on V1 responses are weak or absent in many experiments, contextual inferences in V1 could depend on what task a monkey is doing. For example, let this dashed box be the resident field of a V1 neuron being recorded, and this vertical bar is the preferred input orientation of this neuron. And there are these four surrounding or contextual bars outside the resident field. They should exert contextual inferences on the neuron's response to the central bar. This inference turns out to be dependent on the task the monkey is performing. Let's say that the monkey could be doing one of the two following tasks. In task 1 is to report whether the central bar is closer to the neighboring bar to its left or to its right, and ignore the bars above and below. In task 2, it is to report whether the central bar is to the left or right of the top and bottom neighbors, and ignore the left and right neighbors. Now, when the monkey is doing task 1 rather than task 2, then this neuron's response to the central bar is more influenced by where the left and right neighbors are placed. Conversely, when the monkey is doing task 2 rather than task 1, then the neuron's response to the central bar is more influenced by where the top and bottom neighbors are placed. Contextual inferences in V1 also seem to depend sometimes on monkey's experience. For example, for these two visual input images, the red dashed box is the residual field of a V1 neuron being recorded. The same shaded ball is inside the residual field. In this case, this central ball is the odd one out in its shading. In this case, all the balls have the same shading. Normally, the neuron's response to the central ball does not depend on whether its shading is the odd one out. However, after the monkey has learned to detect the odd ball, then the neural response becomes dependent on whether the ball within its residual field has an odd shading or not. This experience-dependent contextual inference is unlike the usual type of contextual inferences in V1. The dependence on the shading direction is only on the longer latency responses of the neurons, not the initial responses of the neurons. Unlike V1 neurons, V2 neurons are sensitive to the shading direction without any task experience.